Welcome to our presentation on HDFS block management and metadata storage. Today, we'll explore the core mechanisms that enable Hadoop Distributed File System to handle massive datasets efficiently, providing both scalability and fault tolerance. We'll delve into how HDFS splits files into blocks, replicates these blocks across the cluster, and manages metadata to ensure reliability and high performance. The primary objective of HDFS block management is to split large files into manageable blocks. By default, each block is 128 megabytes, although this size is configurable. This approach is optimized for handling very large files, which is typical in big data scenarios. Breaking files into blocks allows for distributed storage across multiple machines, enabling parallel processing and efficient use of storage resources. Moreover, by having a relatively large block size, we minimize the amount of metadata that the NameNode must manage, which is critical for scalability. To ensure fault tolerance, HDFS replicates each block multiple times. The default replication factor is 3, meaning each block is stored on 3 different data nodes. This redundancy allows the system to continue functioning even if 1 or 2 nodes fail. Each block is stored as a separate file in the underlying operating system's file system on the DataNode. This design choice simplifies storage management and leverages the local file system's capabilities. HDFS employs a rack-aware block placement policy to maximize both reliability and performance. Here's how it works. The first replica is placed on the local DataNode if the client is running on a DataNode, or otherwise on a random node. The second replica is placed on a different rack to provide rack-level fault tolerance. The third replica goes in the same rack as the second, but on a different node to ensure inter-rack redundancy without additional cross-rack traffic. Any additional replicas are placed randomly across the cluster, avoiding nodes that are too busy. This strategy balances the cluster load and provides fault tolerance against both node and rack failures. Metadata in HDFS is essentially data about the data. It includes 2 main types: namespace metadata, which describes the file system structure, such as directories and files, along with their permissions and ownership, and block metadata, which maps each file to its constituent blocks and tracks the locations of these blocks on data nodes. For fast access during operations, the metadata is kept in the NameNode's memory. However, to ensure durability, it is also persisted to disk. HDFS uses 2 critical files for metadata storage: FsImage and EditLog. The FsImage is a complete snapshot of the file system metadata taken at a point in time. During normal operations, it is read-only. The EditLog, on the other hand, is an append-only transaction log that records every change made to the file system since the last FsImage. Both are stored in the NameNode's local disk. This combination ensures crash consistency. If the NameNode crashes, we can recover the state by loading the FsImage and then replaying the EditLog. Let's look at the metadata workflow. At startup, the NameNode loads the FsImage from disk into its RAM and then applies all the transactions from the EditLog to bring the in-memory state up to date. During runtime, any changes to the file system are first written to the EditLog to ensure durability, and then the in-memory metadata is updated for fast access. Periodically, a process called checkpointing occurs, where the EditLog is merged with the FsImage to create a new FsImage. This task is typically performed by the secondary NameNode in non-HA setups or by the standby NameNode in HA mode. Checkpointing prevents the EditLog from growing too large and speeds up NameNode restarts. Data nodes communicate with the NameNode through heartbeats and block reports. Every 3 seconds, a data node sends a heartbeat to the NameNode to confirm it's alive. Along with the heartbeat, it may send a block report. There are 2 types of block reports: full block reports, which list all blocks on the data node and are sent at startup and approximately every hour, and incremental block reports, which are sent whenever there are changes, such as new blocks or deleted blocks. Based on these reports, the NameNode can issue commands to the data node, such as replicating a block to another node or deleting a block that is no longer needed. HDFS is designed to handle failures gracefully. If a data node fails to send a heartbeat for more than 10 minutes, the NameNode marks it as dead. The NameNode then checks the replication status of the blocks that were stored on that node. If any block now has fewer replicas than the desired replication factor, the NameNode will initiate replication of those blocks to other data nodes. Additionally, to handle data corruption, HDFS uses checksums. When reading a block, the data node verifies the checksum. If a block is found to be corrupt, the NameNode is informed and will arrange for a good replica to be copied to another node to restore the replication level. In a standard setup, the NameNode is a single point of failure. To address this, HDFS supports high availability mode. In HA, there are two NameNodes, one active and one standby. They share the edit log through a group of independent daemons called journal nodes. The active NameNode writes edits to the journal nodes, and the standby reads these edits and applies them to its own in-memory state. This standby also periodically checkpoints by saving a new FsImage. If the active NameNode fails, the standby can quickly take over, providing automatic failover and zero downtime. In summary, HDFS splits large files into blocks, enabling parallel processing and efficient handling of huge datasets. Replication ensures data durability even in the face of hardware failures. The metadata is stored in RAM for fast access and on disk for persistence, using the FsImage and EditLog mechanism to maintain reliability. And with high availability, we eliminate the single point of failure at the NameNode, ensuring continuous operation. These mechanisms together make HDFS a scalable and fault-tolerant distributed file system.